All right, question 32 on the math subject GRE practice test. This question is kind of fun. We get into some group theory. What we're asked is which of the following sets of complex numbers is not a group under multiplication? So when you're thinking about groups, ideally you know that there's 4 criteria that a collection of elements needs to satisfy in order to earn this title of being a group. First one is you need closure. Take any 2 elements in the set, combine them with the operation of the group. You better get another element in the set. You better have an identity element. That's just an element in the set that you can combine with any other element in the set, again, under the operation of the group, to leave that other element unchanged. So in the case of multiplication, think 1. Multiply a number by 1, you don't change it. For every element in the set, you must have an inverse. And that's just an element that you can multiply, since our operation is multiplication, that element by, such that the product will be our identity element. Finally, the 4th one is you need associativity. And that just says if you have 3 elements in the set, maybe A, B, and C, and you combine the first 2 under the operation of the group, multiplication in this case, and then take that element, which is also in the set thanks to closure, and combine it with that 3rd element, C, you're going to get the same element as you would if you took A and combined that with the element in this set that you get when you combine B and C. What's kind of nice is often you don't need to check this 4th one. If the set that you're considering is a subset of some other set that you know to be a group under that operation, the subgroup would inherit associativity from the group, so you wouldn't even need to check it. You might know that the set of all non-zero complex numbers is a group under multiplication. Sometimes that's written as C star. Not really relevant to this problem, but all complex numbers, non-zero or otherwise, is also a group, but not under multiplication, under addition. This set's not a group under multiplication because the element 0 doesn't have an inverse. There's nothing you can multiply 0 by to get 1 as the answer. The fact that the non-zero complex numbers is a group under multiplication, and that each of these sets is a subset of C star, tells us that if any of these are a group, they would be a subgroup of this group, and therefore would get associativity for free. So when we're trying to figure out which one of these sets is not a group, we shouldn't even bother considering associativity. We know all of these are going to satisfy that. So really what we're looking for is a no in either the closure, identity, or inverse columns for one of these 5 rows. So I think it's easiest to start with the identity element. Because the operation of our group is just standard multiplication, the identity element is just going to be 1. Or if you want, written as a complex number, 1 plus 0i. I fully expected all 5 of these subsets to contain the identity element. I kind of figured not having that would be too easy. For this element, A is equal to 1, B is equal to 0. And sure enough, 1 and 0 are both real numbers, and 1 squared plus 0 squared equals 1. 1 and 0 are both rational numbers, and again, 1 squared plus 0 squared equals 1. 1 and 0 are both integers, and again, 1 squared plus 0 squared equals 1. 1 and 0 are both real numbers, and 1 squared plus 0 squared is certainly not equal to 0. But then when you get up here to part A, 1 and 0 are not positive rational numbers. All right, 0 is not positive. So because 0 is not positive, 1 plus 0i, the identity element, is not in this first set. We don't even need to check anything else. We're done with the problem. A is not a group under multiplication. If this were a test, you'd be moving on at this point. But since this is a video aimed at teaching you all that you'll need to complete your test, it might be worth considering closure and inverse elements for each of these different sets as well. To do that, I kind of think it helps to take 2 different points of view of the multiplication of complex numbers. So the first way that I think most people think of is kind of an algebraic point of view. If you have a complex number like, I don't know, n plus mi, sure. And you have some other complex number like p plus qi, yeah, all right. I really don't want a subscript. That's why I'm involving all these different letters. When I'm multiplying these 2 complex numbers together, I can just kind of think FOIL. So first I multiply their real parts, I get n times p. Then I multiply the real part here with the imaginary part here and get nqi. Similarly, this real part and this imaginary part would yield mpi. And then finally, the product of the 2 imaginary parts would be plus mqi squared. However, as you likely know, I squared equals -1. So the real part of the resulting complex number would just be whatever np minus mq is equal to. And the imaginary part of the resulting complex number, if I factor an I out of each of these 2 terms, would be nq plus mp. That's all true, but sometimes you can save yourself some time if instead of considering this algebraic point of view, you kind of consider a more geometric point of view. I can plot complex numbers by plotting the real part on the x-axis and the imaginary part on the y-axis. So I don't know, if this is n maybe, and this is m, the complex number n plus mi would be right here. And maybe I'll make P negative and put Q way up here, sure. Then the complex number P plus QI would be up here. And a cool consequence of this interpretation of complex numbers is that we can multiply them by just considering the vectors represented by these points. What I'm saying is if you connect the origin to this point here, and you connect the origin to this point up here, the vector that would represent the complex number that's the product of these two, you'd get by just adding their directions and multiplying their magnitudes. Maybe a little bit more formally, if the vector that represents the complex number n plus mi, maybe we'll call that vector v, has a magnitude of v and a direction of theta sub v, and the vector representing p plus qi has a magnitude of u and a direction of theta sub u, then the vector representing the product of those two complex numbers, n plus mi times p plus qi, has a magnitude of u times v and a direction of theta sub u plus theta sub v. What I'm saying is if we throw a 1, I don't know, right here just to scale stuff, then theta sub v would be this angle, and theta sub u would be this angle. What's this one, like 40 degrees maybe? And maybe this is, I don't know, 130 degrees. If I take 40 plus 130, I'd get 170. That 170 degrees, so I don't know, roughly this, would define the direction of the vector representing the complex number that's the product of these two complex numbers. What about the magnitude? Well, I just need to know how long this vector is and how long this vector is. If this is 1, maybe this is like, I don't know, 0.8. And maybe this is, I don't know, 1.5. 0.8 times 1.5 is what, 1.2? I probably could have made this work out easier for myself. So all I'd have to do is draw a vector with length 1.2, maybe that's roughly here, sure, in this direction. And this complex number right here would be the product of the two that we have pictured. In short, to multiply complex numbers, just add their directions and multiply their magnitudes. With this interpretation of multiplying complex numbers, we can quickly see that this first set here not only lacks an identity element, it's not even closed. Because the criteria that a and b are both positive rational numbers really just means that the vectors representing those complex numbers will fall somewhere up here in the first quadrant. But if we multiply together two vectors in the first quadrant, we're not guaranteed to end up with the vector in the first quadrant. Think about if they had directions, I don't know, 80 degrees and 70 degrees. 80 degrees and 70 degrees would certainly leave me in the first quadrant. They'd be elements of this set, but 80 plus 70 is 150. So the product of those two complex numbers would be represented by a vector with direction 150 degrees. It would be over here somewhere in the second quadrant. Not only does this set not have an identity element, it's not even closed. I know this video is getting a little bit long, but this idea of closure that I think you can see pretty easily from graphing can be tied to this algebraic interpretation of multiplication. Because think about how would the product of two vectors escape the first quadrant? Well, we need relatively big angles representing their direction. How do you get big angles representing their direction? Their imaginary part has to be relatively large compared to their real part. All right, this vector here has a small angle because its real part is relatively large compared to its imaginary part. But this vector here has a relatively large direction because its imaginary part is relatively large compared to its real part. Anyways, if we multiply together two vectors with relatively large imaginary parts and relatively small complex parts, then the m and the q are large and the n and the p are small. But if the n and the p are small, the product of n and p is pretty small. And if m and q are large, the product of m and q is pretty large. So I'm taking a small number and I'm subtracting a large number. I'm going to end up with a negative number here. A negative real part with a positive imaginary part, because the product and sum of positive numbers is positive, would leave me over here in the second quadrant. While we're focusing on this first set, which is certainly not a group because it doesn't have the identity element nor closure, we might want to consider whether it even has inverse elements. Turns out it doesn't. Wait, how do you know that so quick? Did you do a bunch of algebra in your head? Nah, I just considered this graphing application. What would the vector representing the inverse of this complex number look like? Well, I know that when I add the direction of this vector to the direction of its inverse, I need to get 0. Why? Because the product of an element and its inverse is the identity element. And the identity element, as we already figured out, is 1 plus 0i. 1 plus 0i is right here. The vector representing 1 plus 0i is shown right here. The direction of this vector is 0. To get a sum of 0 from the two directions, I need the direction of the second element to be the opposite of the direction of the first element. If my first element is represented by a vector in the first quadrant, the inverse of that element would have to be represented by an element in the fourth quadrant here. I think I said this magnitude was 0.8 before, so I'd need a number a little bit bigger than 1, so that 0.8 times this number is equal to 1. But more importantly, I'd need a direction, so that when I sum it with this direction, I get 0. That would leave me down here in the fourth quadrant. In the fourth quadrant, b is not positive, so the inverse of this element n plus mi would not be in this set. In fact, maybe you can convince yourself that the inverse of every single element in this set is going to live down here in the fourth quadrant, and therefore not be in this set. Not only is there an element that doesn't have an inverse, which is all that we need to decide it's not a group, there aren't any elements in this set that have an inverse in this set. This couldn't be less of a group if you tried. Before ending this video, I just want to quickly talk about how options B, C, D, and E do fit all these criteria. C, D, and E are all kind of similar, so first let me knock out B. Set B contains elements a plus bi such that a and b are real numbers and that a squared plus b squared does not equal 0. In other words, all non-zero complex numbers. The only way a squared plus b squared equals 0 is if both a and b are equal to 0. In other words, if we're talking about the complex number 0 plus 0i or just 0. Do we have closure? Yeah, absolutely we do. Kind of from this graphing element would probably be the easiest way to see it. Although you could also get there algebraically. It would probably be a pretty fun algebraic proof. I need this to equal 0 and I need this to equal 0, so this would equal this and this would be the negative of this, but therefore, plugging in, solving, you'd be able to show that either n and m are 0 or p and q are 0. I'm not going to go through that proof. I prefer the kind of proof by picture. You take two non-zero vectors, add their directions, multiply their magnitudes. That defines another non-zero vector. That non-zero vector represents a non-zero complex number. I get closure. For closure for C, D, and E, I kind of think about it as two steps. Let's first focus on a squared plus b squared being equal to 1. Well, if a squared plus b squared equals 1, the magnitude of the vector is 1. So if I multiply two complex numbers whose vectors have magnitude 1, the vector representing the product will have magnitude 1 times 1, which is 1. So a squared plus b squared will be equal to 1. Right, but what about integers or rationals or reals? Well, maybe then it's easier to take this algebraic point of view. If n, m, p, and q are all integers, n times p is an integer and m times q is an integer, and the difference in integers is integers. By the same logic, nq plus mp is an integer. Repeat exactly what I just said, except exchange the word integer for the word rational or real, and you'll get kind of the other half of closure for C, D, and E. Finally, inverses. Again, multiple ways you can figure it out. Arguably the most straightforward is to take your arbitrary element, n plus mi, and multiply it by its inverse, maybe n prime plus m prime I, sure, and say that that product is equal to 1. I want to know what n prime plus m prime I would be equal to. We'll divide both sides by n plus mi. Maybe you're like, yeah, but this isn't a complex number. Well, it is. It's just not written in the form that you want. A little trick to get this into the form that you want is to multiply by the conjugate. So we'll multiply the top and the bottom by n minus mi. That leaves us with n minus mi up top. And as you can verify by foiling n squared plus m squared down on the bottom. Another way of writing this is it's n divided by n squared plus m squared plus negative m divided by n squared plus m squared, all times I. What I'm saying is the inverse of n plus mi is just n over n squared plus m squared plus negative m over n squared plus m squared I. If we consider set E here, n and m are real numbers. That means this will be a real number and this will be a real number. We get this half of the statement from the graphing and this half of the statement from kind of the algebraic representation. We get inverses. Same logic, except exploiting the fact that the square and product and quotient of rationals will produce rationals gives us this half for statement D. We get inverses as well. For C, you got to be a little bit careful. You might look at this and be like, wait, just because n and m are integers doesn't mean that n divided by n squared plus m squared is going to be an integer. That's true, but these aren't just any integers. They're integers such that a squared plus b squared equals 1. So really, there's only 4 elements in this set. Either a is 1 and b is 0, in which case we're talking about the element 1, or a is 0 and b is 1, in which case we're talking about the element I, or a is negative 1 and b is 0, in which case we're talking about the element negative 1, or a is 0 and b is negative 1, in which case we're talking about the element negative I. Hopefully I said those all right. For part C here, rather than consider this expression, it might be easier to just verify that each of these elements has an inverse. The inverse of 1 is 1 because 1 times 1 is 1. The inverse of I is negative I, because I times negative I is negative I squared. In other words, negative negative 1. In other words, 1. The inverse of negative 1 is negative 1, because negative 1 times negative 1 is 1. And as we already talked about, the inverse of negative I is I. We got all our inverses. I'm losing track of what I've even talked about. I'm ready to be done with this problem. You're probably ready to be done with the video if you haven't quit it already. But we also get inverses up here. Maybe the geometric argument is the easiest for this. Pick any non-zero vector you want. I don't know, this one in red maybe. Figure out its direction, draw a new vector with a negative of that direction. Figure out its magnitude, draw a new vector whose magnitude is the reciprocal of this vector. The product of those two vectors will give you the identity element. And because any non-zero vector in our coordinate plane corresponds with a non-zero complex number with real parts, we get our inverses here. It looks like B, C, D, and E are all groups, but A is not.